Alright, so we're going to estimate the instantaneous rate of change of this function at x equals 1. So what this graph looks like, it's a parabola, and x equals 1, the x-intercepts are, so this is 1 is here, and the turning point occurs at 2. So that might be helpful to know. So I guess I'll leave this up to you guys. Where should we start? What's a good place to start to try and estimate an average? Sorry, well, we want the instantaneous rate of change, but we can't get the instantaneous rate of change, okay, because we need, the only way we really know to do that is to pick an average of 2 points that are really close together. So just like that speed camera we were talking about, we think it's an instantaneous, but it's actually taking two snapshots really, really close together and judging the distance over, you know, a tenth of a second or whatever it is. So let's start. Let's work out what the y value is first. So let's make it a function, f of x. So at x equal 1, we have f of 1 is going to be 4 by 1 take 1 squared, which is 3. So we have this point here, which is 1, 3. Now let's say, if I take the average between 1 and 2, okay? So this average here, now, do I have a piece of wood? Yes, broken rule, perfect. Now this is the, if I were to plot this, you can't really see that. If I were to plot this, that there, now my parabola isn't perfect, but where I've got my ruler now, like that's the gradient line. Sorry, the tangent line. So the instantaneous rate of change is the gradient of that tangent line. You guys agree with that, right? Now the line that I'm calculating the gradient for is actually this line here. So I've drawn this tangent line as the average between this point and that point there. Is that are they pretty close? Like they're not like on top of each other perfectly, but they're pretty close. Like it's not like this one, and like if I use the line like that, that's almost perpendicular. So it's pretty close. So it's a good start. So let's do so f of 2. Which is 4 by 2 take 2 squared, which is 8 take 4, which is 4. So this point here is 2, 4. So our gradient, we'll do m. We'll call this instantaneous rate of change m. So m is going to be the change in y, so 4 take 3 over 2 take 1. So that's 1 on 1, which is 1. So that gradient there is 1. So are we happy with that estimate? In the video there? Yeah, no? How could we improve it?
What if it's like how you had the graph that was like going up and went like sideways? Wouldn't that mean it was really different?
That's a cubic.
Yeah.
So let's leave cubics alone for a little while. Okay, but how could we? What I want to know is I've got an estimate for my rate of change at this point, so the tangent at that point. How can I improve my estimate for it?
You could average out that gradient with the gradient from the origin to the point.
Yeah, I could. I really just want to, like, our suggestion is we just take an estimate closer. Okay, so how could we improve this? We could move this dot here. This dot is fixed. That's the point. This is the point where I want to know the rate of change for. Okay, I could improve my line here by moving this point a bit closer, couldn't I? Okay, so let's do a redraw. So I should add, this is when I'm writing m equals, this is really m is approximately equal to. Okay, because this isn't exact. So I'll draw my line again. I'll try and make it a bit more of a parabola. Oh, that's still not great. Just ignore that line. Not having a good day.
It's a double rainbow.
Okay.
Oh my God.
I'm going to draw a segment of the curve. So this is my point here. This is 4, 2. This is the top, and this is 1, 3. Is it 1, 3? Yeah. It is 2, 4. Okay, so rather than going to x equals 2, where could I go? Split the difference? X equals 1.5? 1.5? Okay, so we'll go m. So f of 1.5 then is 4 times 1.5 take 1.5 squared. What's that equal to? That's 6 take something. 2.25. So is that 4 point something? 4.75? 3.75. 3.7. There we go. 3.75. Okay. So our gradient is roughly equal to, in fact, it's it's f of 1.5 take f of 1 over 1.5 take 1. So what's 1.5 take 1? 0.5. And this is 3.75 take 3, which is 0.75 on 0.5, which is 1.5. So basic arithmetic there. Okay, so our gradient, we guessed it was 1. Okay, and it's actually, we think it's even closer to 1.5. You guys agree with that? Yeah? Okay. Are we happy with that then? Or do we want to make it better? Let's see, I just want to highlight a few things here. I'm going to try one more time to draw this. That's not too bad. If I take my point, so I've got my point 1, 3. Thank you guys. I'm going to add in a distance called h. So I'm going to put this point here. So this point here started at the turning point and we moved it a bit closer. We moved it to about here. So that was 1.5, 3.75. Now that point there, I'm going to call that whatever. So I have x equals 1 here. I'm going to call this 1 plus h. So I'm going to add on h to 1. So that means that this distance, that distance there, which is completely straight, that distance there, we'll call that h. Okay, so then here in the first one, h was 1, because there was a distance of 1 between the dx values. And then here, and then on the numerator that's 1, and then in the next one it was 0.5. So h is whatever I'm adding on to my original value. And then my values here, this is f of 1, which is 3. And then this is f of whatever this is. So this is f of 1 plus h. You guys see that? So f of 1 plus f of 1 plus h. So we could really say that m, so our instantaneous rate of change, is approximately equal to f of 1 plus h minus f of 1 over h. Because this is really 1, well, it's 1 take away, no, it's 1 plus h take away 1. So they cancel out, and this is the h. Because we always end up with the 0.5 on the bottom or whatever it is. Okay, so we could use this formula here, okay, to approximate our instantaneous rate of change at, what was it? At x equals 1. So let's do two more values. Let's do two values for h. So what's another value for h? How could we make this a bit closer? We do we'll do 1.1 even. 1.1. 1.0. I want to do 1.1 first. I'll do 1.1 and then we'll go even smaller. So let's let h equal 1.1. I'm a bit all over the place here. Yep.
How small does the distance between the 2 points have to be for it to be considered accurate?
You're skipping ahead there. Okay, we are going to talk about that. How small does the difference between, how small does h have to be for us to consider for us to judge that we have an exact value for?
It depends on the specific equation.
Yeah. Let's see what happens. Let's do 1.1 and then we'll do something even smaller. So let's do m is approximately equal to f of 1 plus 1.1, so 2.10. F of 1.1, take f of 1 over 0.1. So f of 1.1 is, let's do it over here, f of 1.1